This begins chapter 28, dealing with Einstein's theory of special relativity. We'll start with this equation. Delta M is a change in the mass of an object. It could be positive or negative. The mass can increase, the mass can decrease. Q is the associated quantity of energy gained or lost by the object. C is squared. Here's an example of a 5 kilogram object gaining energy, in this case potential energy, gravitational potential energy. 5 kilogram object on the ground floor is pushed up a 10-meter tall building. The gravitational potential energy increase is mgh, works out to 490 joules. This equation predicts that the object's mass will have changed by this amount, Q over C squared, a very small number. No wonder we never notice such a change in mass. The other equation, just the reverse of this equation, states that when the mass of an object changes, either by increasing, which makes delta M positive, or by decreasing, in which case delta M would be a negative number, there's a corresponding Q, or quantity of heat, that is liberated or emitted or released from the object. On the other hand, if delta M is positive, then the object's quantity of energy increase will be some positive number. Let's discuss the first case in which the change in mass is negative. The object loses mass. That happens in perhaps the second most important type of mass energy equivalency, you can call it. When a certain type of uranium, that's called an isotope of uranium, I won't mention what it is until a later chapter, when it's caused to undergo fission, a splitting apart into two crudely equal or roughly equal halves or parts, the amount of mass you started with that uranium nucleus is not what you end up with later. It's not that parts of it flew away and you can't find it. It's just that if you did find all the parts that are left when uranium undergoes this splitting or this fission, add up all the masses of the parts, it's less than what you started with, which was a uranium nucleus. Now, the amount by which it's less, some negative number, is shown here. Delta M is a very small number. Now, the Q associated with this delta M, shown here as the amount of mass loss times the speed of light squared, gives you a Q value that's negative, a very small number. The negative sign means that energy is released from that place, from where that uranium nucleus was. You end up with some objects left behind, bits of matter, but flying away from that location can be high-speed particles with kinetic energy. Likewise, flying away from that location can be electromagnetic waves, electromagnetic energy. The total energy each time one of these events occurs is that number. It's small, but if you can make uncountable quadrillions of uranium nuclei to do the same thing, you're talking about an amount of energy capable of leveling an entire city, such as Hiroshima. We'll talk about the so-called atomic bomb in chapter 30. That's it for now.